So last class we were discussing the basics about transport of pollutants in air, the issues of stability. So we looked at three different cases: unstable, neutral, and stable. So unstable conditions, essentially the main conditions under which unstable atmosphere exists is we have high thermal and mechanical. High thermal, what we call is the adiabatic. In the sense, we have to revise this statement. We have high mechanical turbulence, which means there is wind is very high. That is one. Turbulence essentially means wind is in all directions. It is the turbulence. The hallmark of turbulence is there is high velocity in the x direction, but it also in z and y direction also it is fairly high. So this is one. Then the adiabatic lapse rate. So we see conditions like this. Essentially we are seeing these two things. The slope of delta. So when we have unstable conditions, we see a scenario like this. This is the adiabatic lapse rate, and this we expect to be the environmental lapse rate. Yeah, so if you look at the this thing, this is temperature and this is height. So minus dt by dz. So if you look at this in this direction, if you plot the temperature as a function of height dt by dz, where this is on the y axis and this is on the z axis, the slope of minus dt by dz, the negative slope of this, there is a greater temperature decrease. So it is essentially this T adiabatic is greater than T environmental. So in the other case where we have neutral conditions, here no thermal effect. Which means essentially it is T adiabatic is the same as environmental. So it is purely dependent upon the mechanical turbulence that is there. So just velocity. Stable conditions, we have inversion. The T adiabatic is less than environmental, which means that under stable conditions we have Z like this. Okay. So how does this affect pollutant transport? We started discussing this a little bit last class.
Excuse me, sir. Sir, in the first graph, again, temperature of environment is greater than temperature of adiabatic.
Oh, sorry. This is the other way around. You're right. Yeah, so this is correct. So you keep going up, this parcel keeps going up and up. or the other way around. It is also valid if it is like this, because in this case if you push it down it keeps going down, that is also possible. So, either way, either of these things can happen. The neutral is when neither of these are effective. Okay. So, yesterday's graph we saw in the PowerPoint, the stable condition occurs where unstable condition occurs in this direction, in both this. See here it is greater, it is lesser. So, it keeps going up depending on where it is. If it gets pushed, it will keep going in that direction, where depending on what the temperature profile at that point is. Now, the significance of this particular graph is in terms of the so what we showed in that graph is with reference to what is called as the mixing height. So, for essentially, if you look at the relationship between adiabatic and environment, it does not matter if lower or higher. If it gets pushed, it will go to the other direction, whichever direction is favorable. So, if it is on this one, if it gets pushed, it will keep going up. If it gets pushed here, it will keep going down. Okay. So, with the relevance to environmental thing comes when there is a mixing height. So, we will look at that in a bunch of in a series of images. So, in the last class we started talking about this is a stack or a source. This is a very classical stack that is given. So, this is ground level. And the stack is releasing some pollutant, and the general this thing we see is this kind of behavior. So, this is what we when we look at an ideal behavior of a exhaust of emission coming out of any source. Something happens to it, it spreads over distance. So, this is the, so if we call this as x, and we define this axis as z, this axis as x, and the transverse axis is y, which is along the ground. So, the ground is x and y, and the height above the ground is z. Okay. So, now the boundary, the exhaust starts here, it is coming as a pocket here, and it is expanding, and it is expected to expand. So, and it can go in any format, and that we will see that in a minute. The boundary that is occupied, that sets the limit to the pollutant, is called as a plume. This is called as a plume. So, the shape the plume takes depends on a few of the factors we have discussed. So, whether there are stable conditions or unstable conditions, and depending on where the mixing height and all that is. So, in terms of that. So, the relevance to mixing height is following. So, if you have, we have discussed that if you have the environmental lapse rate and we have an adiabatic lapse rate like this. So, at some point here they intersect. So, the air parcel, if the adiabatic lapse rate is here, this is the temperature of the pollutant source is here, and this is the ground temperature of the environment. The parcel is moving in this direction, it will not go beyond this point. That is the general idea. So, if it is on top here, it will keep going out. If it is on bottom here, it will keep coming down, but it will not cross this line. So, this line here, if you look at it, that this parcel as it goes up, it becomes heavier. So, it will come back here, it cannot cross this. So, that is the definition of this mixing height. And we saw because this environmental lapse rate keeps changing throughout the day, this temperature keeps changing. So, this line will change throughout the day, and that because of that the mixing height also will change. So, if these two lines are, so there may be a case where you may have the environmental lapse rate that looks like this, then this is always lower, then this is usually not, most of the times it is the other way around. So, we have a problem here. If it is here, then we have a big problem. So, this can occur sometimes. in some cases where the pollutant is very there is no buoyancy at all, it will stay there. So then there is no thermal effect is not really felt in this case. But usually normally when you look at pollutants like exhaust, which is higher temperature than the ambient most of the times. So it is very likely that you will see this kind of behavior. A lot of times you will see this kind of behavior. You can see that sometimes they will diverge. They will diverge, which when they diverge, which means that the mixing height is almost infinite. There is no ceiling. It keeps going up. It can go as much as it wants. The only limiting factor there is the velocity, the wind. The wind will take it. Scale of turbulence is high. It will keep going up as high as possible. Okay. So keeping this in mind, there are a few cases of plume behavior that people have classified, categorized as, and we will just go over that a little bit. So these are different scenarios, scenarios where we have the definition of mixing height, where it, how it can occur and all that. So we have different types of plume shapes that it can take, and the two main factors here. So we will go over each one of them. The first one is called as looping. It's a super adiabatic lapse rate, which means that the lapse rate is greater than the this slope of this line minus dt by dz is greater than this one. No, super adiabatic means the environmental lapse rate is greater than this. Okay, that's only because this one doesn't change. Adiabatic lapse rate stays where it is. The other thing changes. So you can see that this line is. This is the environmental lapse rate, and this is the adiabatic lapse rate. Okay. Now here you can see that the wind speed is quite high. In this left hand, this part of it indicates the wind speed. So it is very high winds, large eddies. So what you can see is when as soon as it gets out, because of the super adiabatic lapse rate, which means very unstable conditions, it is going to accentuate, exaggerate wherever this thing is going. It's going to move up and down accordingly. So it pushes it up, it goes down, it goes up, goes down, goes up. The variation of the delta, the z variation of the plume is very high because of this particular this thing. In the next this one is called as coning. This is neutral, which means there are thermal forces don't play a big part in this. The thermal forces are really the adiabatic, the environmental lapse rate is almost the same as the adiabatic lapse rate, approximately the same. So there is not a big exaggeration of the vertical of the movement caused by wind. So the wind, the turbulence of the wind results in large eddies. Eddies means the velocity. When you have turbulence, the velocity of you have velocity Vx component, then there is Vy component and a Vz component. You have a mean Vx plus fluctuation in all three directions. The velocity is not just one single average single number. It's a fluctuation of these two things. Okay. In all three directions, but this is the direction of the wind, but there is also a fluctuation in the other two directions, and the extent of this is that determines what is the amount of mixing that happens, and this is in general terms this is called as dispersion. In chemical engineering literature, this is called as dispersion. It's all back mixing. Any presence of any eddies results in a back mixing, and that is termed as dispersion. This is not to be confused with another term called diffusion. Diffusion is a different phenomenon. Dispersion is mainly because of these eddies, the circulation patterns that are formed. So here because of the so this part is always there. The amount of spreading as a result of this eddies is occurring because of the velocity. In addition to that, we have thermal forces that may exaggerate it or suppress it. Both of these things can happen. Okay. So there is dispersion in the x direction, there is dispersion in the y direction and the z direction. All these three are there. So in coning we do not have this thermal, so there is no thermal effect on it. So it is just the dispersion. This coning will give you what is the effect of only velocity. Okay. So this will give you this very classical plume shape. So it is increasing nicely in one direction, in the direction of wind. The wind is in this direction, in x direction, and it is going in that direction, and it is spreading. So this spreading is not just in the y, it is not just in z as shown in this picture, it is also in the y direction. So normally we will come to the shape of the plume. The plume itself has, it is a 3-dimensional plume. It is like so in the cone, the reason it is called coning is, if you look at it from this direction, from the along the x axis inwards, you will see that it looks like this, it looks like a cone. It takes the shape of a cone, okay, and so in the center of the cone is your source. So it looks, this is I do not know if you can imagine the shape of this. So in the center of the cone is your source. So which means there is a certain amount of y dispersion, there is a certain amount of z dispersion also. The next condition, here you can see again that it is still, there is no mixing height, does not come into play here because there is no ceiling, they do not intersect at all. So it is again, there is no limit to this. The third condition is called fanning, and now you see here that the adiabatic lapse rate and environmental lapse rate intersect, but they intersect right below the source, just below the source. These are all different scenarios, and you can create any number of scenarios depending on where the source is and what is the lapse rate. These are just examples, some possibilities, common scenarios. So you can see that this is the mixing height, but you also, so the pollutant source is right above this mixing height, okay. So if a pollutant is released, it is following this line, but you see that in this particular instance the temperature of the plume is less than that of the environment. So it tends to sink back to its source point, or it sinks back to the mixing height. So it stays very close to the mixing height and it goes in this direction. The reason it is called fanning is the z dispersion is now suppressed because the thermal adiabatic lapse rate, environmental lapse rate are such that it does not allow the parcel to go up, but it can still disperse in the y direction. So fanning is, if you look at it from the top, it looks like this. This is a source, it is still fanning out. This is y direction is fanning, but the z direction dispersion is very small, very small. So in this zone the concentration is likely to be very high, but it does not spread a lot. It does not spread in the y direction, it does not spread in down below also, it is there. Sometimes you can see this very clearly on certain days, which in this case you can see that when this kind of scenario occurs, you can see, if you look at chimneys sometime, you will see a very straight plume like this. It is very rare to see it, but sometimes you can see it if you are going in factories in certain seasons probably. So this kind of behavior occurs when the source is very high temperature and it is at the higher height, and then see this behavior occurs only during inversion, it is in the early mornings. So you can see that sometimes very early mornings. So but this is not really bad because from a point of view of exposure, if it is going to stay like this, your receptors are somewhere here on the ground, so it will not come down, it will stay there. This will be a problem if the source is here. The source is inside below the mixing height, then it will go up, then it has nothing, nowhere else to go, and mechanical turbulence will spread like this. It is there, it is one of the cases that it is there in this particular case where we have called as fumigation, where it is exactly the opposite. There is inversion there, so it does not matter whether this is like this or it is like this, that is the same thing. What happens here is the ceiling is right above the source. Yeah. So whatever is released will now get contained in this zone because it has to spread. Even if the thermal spreading is not there, mechanically it will spread, and this is called fumigation. This is the most dangerous of all the cases where this is the volume. See, our goal is to maximize the volume in which the pollutant is contained, and this is limiting the volume, which means that concentration will be high, which means effect will be higher. And this occurs during inversion. All kinds of inversion, this is true. It's not just this particular case. It's also this kind of behavior also will happen. Then there is this scenario where it's called as lofting, where it's similar to fanning, but the mixing height is below the source, which means that it will not come below that. But above the source, it is like a neutral or unstable environment, so it can spread. It can spread nicely there. So this is a good scenario because it's not coming anywhere near the ground and it's spreading upwards. So even at some point, if it comes down, its concentration is already reduced quite a bit. Okay. And the last one is called as trapping, in which it is there are two inversions, double inversions, and therefore there are two layers. And if your source is in between that, it will get trapped there. So these are, you can derive a large number of scenarios where this can happen. Okay. The environmental lapse rate keeps changing. Usually this double inversion doesn't happen that often. Under very special circumstances of whether it happens. But normally this regular inversion happens on a daily basis in very cold places. But this double inversion is a little rare. Okay. So it gives you some idea about how to predict where what will be the general behavior of the plume given a set of conditions. Okay, so now I will go back to your this thing. We will now. Any questions on this related to that? So the mixing height, sometimes you have to calculate the mixing height, which means you have to calculate estimation of mixing height is simply this. So you have to take the environmental lapse rate at that point and the adiabatic lapse rate. Let us say that you have some scenario like this, and this is adiabatic lapse rate. This is the environmental lapse rate. So which means I need environmental lapse rate, the temperature profile is measured on a daily basis usually. People measure this by sending out balloons and all that. So there is a balloon that will go up, it will measure temperature profiles every day. Meteorological department does that, a few other labs around the world do it. So there is a report of temperature profiles and velocity profiles, everything that is measured. And so there is seasonal record of it in a given location. So people have this kind of information. Adiabatic, dry adiabatic lapse rate, of course, is a fixed thing. So this is we said that is minus 9.8 degrees centigrade per kilometer. This is the theoretical number. But the adiabatic lapse rate that you normally find in the environment, so this is again changes from place to place. Sometimes it is the air mass is wet, it is not dry, which means that there are other processes that may happen. So the actual adiabatic lapse rate will not be minus 9.8, it will be less than that, it could be around 6 or 7. This has to be measured, or if you can model it, if you know enough about the system. It is still assumed to be adiabatic. Sometimes this you can even get rid of the adiabatic. You can simply say that the lapse rate itself. This is the lapse rate of any pollutant mass. If there are ways to measure it, you can actually get the lapse rate there. So you have to understand one thing, that because there is a lot of fluctuation, there is a lot of error in these kind of estimations. So people, it is very difficult to estimate this accurately. So they get a fair idea that you know where it is going, and that is I think reasonable. Because like you are not getting into weather prediction, because you are predicting meteorology. Environmental lapse rate prediction is meteorology, and prediction of the adiabatic lapse rate also is meteorology in some sense, because it is influenced by whatever is going on around. It is linked to what is there in the environment to some extent. So these are all we have to start somewhere. So, this is an ideal way to do it is the dry adiabatic lapse rate, but be aware that you may not have minus 9.8 degrees centigrade per kilometer all the time. It will be something else, but it will give you a fair idea whether what will happen to a pollutant, what is likely to happen to a pollutant, what are the general scenarios, and then you can build up on that scenario by making more accurate assumptions. So, usually we just calculate the height at which these two intersect, that is the mixing height. Okay. So, you can do it graphically or by finding the intersection of these two equations. I do not think I need to give you an exercise, but we will have a small exercise problem later in the tutorial just to calculate this. So, typically what we do is the environmental lapse rate is based on measurements. Okay. So, there people measure at different heights. The adiabatic lapse rate is based on the surface temperature, the temperature at which the source is originating. So, if it is and this is a bit tricky because this is okay if you have this the source is from a single particular location. Okay, this is where I think we need to define a bit something about the sources. Okay, this a particular source, if you can pinpoint what the source is, okay, it is coming from one particular facility or a factory or a process. We call it as a point source. So, for example, if you have a big factory and there is one stack, one chimney that is releasing all the pollutant from that factory. So, you know that is a very specific source, it is a point source. But if you look at some other kind of sources, look at a road for example, the road it is a long road, a lot of vehicles are moving around. Okay. So, if you look at it from a point of view of a map, if you are looking at a map, the road is a line and there is emission coming at each point in the road, every point in the road. And the amount of emission depends on the number of vehicles that are moving and the emissions coming from each of these vehicles and whatever that is. So, there is an overall emission rate that is coming from this entire line source. Okay. So, these kind of sources is classified as a line source, and then we have area sources, which means that an entire city can be an area source, or you have a very large cluster of industries, they are all releasing next to each other. Okay. So, this is an area source. You also have something called as a volume source, but it is very rare. Volume source means you have a large volume from which emission is coming out. Typically things like a landfill or some such thing, you can consider a landfill as an area source or a volume source depending on how you are looking at it, but volume source is significant if there is a significant amount of z direction also. Volume source is something like this, if you have a big chunk like this and emission is occurring all over all three dimensions, in the x, y and the z, then you may have to consider it as a volume source. For example, if there is a big mountain and then there is a lot of things going on, there is a forest fire or some such thing, so which is a big mountain, that is a volume source. Usually volume sources are rare, but for completion people also have this. So, point sources are something very specific, you can, it is there, it is coming from there, it is not anywhere else, it does not move in place and all that. So, if you have a point source, you know exactly what the temperature is and where it is and all that, what the height is, but if you have a line source for a road for example, you do not know the exact emission temperature, but this emission is mixing with all the other emissions and then going up, it is a combined emission. So, people generally cannot take the temperature of that exhaust there, so because it is mixing and as a group it is going out, and this is not very well understood, but people have measured temperatures at the surface of roads. Okay. This is not the temperature of the environment. Yeah. Temperature of environment is there are no vehicles and you measure the profile, you will get one reading, but as soon as vehicles start moving, the road temperature will change, surface temperature, 1 meter above the ground, the emissions are all mixing, temperature is slightly higher than if you go and measure the environment temperature at say, for example, if I measure temperature on Sardar Patel Road, the main road outside our campus, and then I come inside and measure in a ground where there is no vehicles, it is going to be different, profile is going to be different, there will be a slight increase in temperature at the surface, because, but that is not to be considered as environment temperature, that is to be considered as the starting point of the adiabatic line. Okay. So this is a very difficult thing to especially for area sources to fix what number, but that has to be based on measurement. But for point sources it is very straightforward. You can go put a thermometer there or a thermocouple there and measure what is it, that is it, that is the temperature of the source.